Hello and welcome to yet another lecture on power generation and economics. Paper code PE 704C. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is constraints in unit commitment. Lesson objective. After end of this topic, students will able to distinguish between different constraints in unit commitment. So constraints in unit commitment. We have already know about the conception of unit commitment. Keeping in mind the economical approach, which unit or units we have to run in order to meet the load demand, and also which unit we have to shut down, again keeping in mind the load demand and also the economic criteria that already we have seen in our previous lecture. We also know why this unit commitment is required, and we have also seen that there are some constraints that is there in order to approach to the unit commitment, keeping in mind the economic cons- criteria. So our objective is to meet the load demand by the unit commitment, keeping in mind the conception of economical approach, how economically we can able to meet the load demands. So we are starting with the introduction. It is given that many constraints can be placed on the unit commitment problem. Each individual power system, power pool, reliability council, and so forth may impose different rules on the scheduling of units depending on the generation makeup, load curve characteristics as such. So depending upon the conception of generation to make up and also the load curve characteristics, this is one of the important phenomena that what are the maximum load that is there within the system, or what are the minimum, what is the range between the maximum and the minimum load is there in order to meet the demand of that particular area or the particular day of an area. This is the important criteria in order to comment on the unit commitment. So the one of the important factor is that the spinning reserve. So what that term means, spinning reserve. Spinning reserve is the term used to describe the total amount of generation available from all units synchronized, that is spinning. Means when the all units are in synchronization condition, that is called the spinning. So there are two terms, one is called the spinning and one is called the reserve. So spinning means that all units are in that synchronized condition, that is called the spinning on the system, minus the present load and the losses being supplied. So spinning means all the units on the system are in synchronized condition, and reserve means the total amount of generation that is available from the all units when on the system when they are synchronized condition minus the present load and losses being supplied. So this is the amount of reserve which is there within the system. So the next question will arise that why this spinning reserve is required in the system. Yes, we know that the conception of the spinning reserve and what is spinning and what is the reserve and why this combination of the spinning reserve means. But now a question will arrive that why this spinning reserve is required in the system. Spinning reserve must be carried so that the loss of one or more units does not cause two per a drop in the system frequency. So it is means that when the alternators or to say the units are in synchronized condition, when they are rotating in the synchronized condition, the frequency of the system remain constant. So if one or two units goes out from the system, means there is a loss of one or two units. It will affect the system frequency because we all know that the omega, that is the angular velocity of any alternator, equal to 2 pi into f, that is the system frequency. So, in order to run the entire system in a constant frequency, we have to utilize or we have to provide the conception of spinning reserve in the system. So, spinning reserve must be carried out so that the loss of one or more units doesn't cause to a far drop in frequency in system frequency. So, quite simply, if one unit is lost, there must be ample reserve on the other units to make up for the loss in a specified time period that I have already told. Say one unit from a system is lost. When one unit of the system is lost, the synchronization condition of the entire system is disturbed. So the spinning reserve will be such that we have to counter that particular loss of that unit so that to maintain a constant frequency within the system. Spinning reserve must be allocated to obey certain rules, usually set by Regional Reliability Council in case of the United States, that specify how the reserve is to be allocated to various units. So it is the Regional Reliability Council that specifies that how much reserve will be there by obeying certain rule in order to counter the loss of any unit. So it is predetermined and it is obey some certain rules that is obeyed. So typical rules specify that reserve must be a given percentage of forecasted peak demand. So that reserve must be capable of making up the loss of the most heavily loaded unit in a given period of time. So it is clear that generally the rules is that we have already told that the load pattern or the load characteristics that we have get. So for that load characteristics, we will must concentrate on the peak demand of that particular system. When I concentrate on the peak demand of that particular system, so depending upon the peak demand or the forecasted peak demand, if I make that reserve, so we can capable of counter that particular peak demand. So peak demand means there is a maximum demand. So within the range of minimum demand to maximum demand, we can counter that particular loss in the system or most heavily loaded unit that is lost within the system. We can counterattack if I design the reserve in such a way, yeah, for the percentage of forecasted peak demand. If I keep in mind the percentage of forecasted peak demand, we can easily counter the loss of heavily loaded unit for a given period of time. Others calculate the reserve requirements as a function of probability of not having sufficient generate to meet the load. So, based on the percentage of forecasted peak demand, we have to design the how many reserve that we have to require for loss of the unit, means the heavily loaded unit for a given time period. So not only must the reserve be sufficient to make for a generation unit failure, but reserve must be allocated among fast responding units and slow responding units. So we have to first classify, we have to first determine that which unit is responding fast and which unit is responding slow. So after classifying those units, we have to allocate that reserve. So it is clear that the reserve is sufficient to make up for a generation unit. Not only that it is sufficient to make up a generation unit failure, but also the conception of slow responding unit and the fast responding unit must be allocated in order to comment on the reserve. Because this allows the automatic generation control system to restore frequency and interchange quickly in the event of generating unit outage. So it will help us uh, in order to obtain the automatic generation control system to restore the frequency and interchange quickly in the event of a generating unit outage. Beyond spinning reserve, the unit commitment problem may also involve various classes of schedule reserves or offline reserves, because along with the spinning reserve there are various classes of schedule reserve and offline reserves. These include quick start diesel or gas turbine units, as well as most hydro units and pump storage hydro units that can be brought online, synchronized, and brought up to full capacity quick. So it means that the quick start that I have already, the fast responding unit, that means the quick start diesel or gas turbine units, as well as the most of the hydro units and the pump storage hydro units that can be brought up on the line, and they have to synchronize, and they have and brought up to full capacity so quickly. That is the fast responding units that we have to keep in mind in order to do the spinning reserve consumption. As such, these units can be counted in the overall reserve assessment as long as their time to come up to full capacity is taken into the account. So means the amount of time is required in order to make those units come up to their full capacity is also taken into the account. So this is the another important criteria in order to design the conception of spinning reserve. So if say now we are taking a problem, that the problem is that if we are to supply a load of 550 megawatt, what unit or combination of the units to be used to supply this load most economically? Okay, to solve this problem, simply try all combinations of the unit. Some combinations must be feasible, and that we have known that some combination will be feasible and some combination will not feasible. So the reserve that is finally must be spared around the power system to avoid transmission system limitations, often called bottling of reserves, and to allow various parts of system to run as island, so they became electrically disconnected. So in case of the uh, unit commitment, to must paired around the power system to avoid the transmission system limitations, which is often called as bottling or reserve, to allow the various parts of the system to run such as iron so that they became electrically disconnected. So now I am taking that we have already seen in our previous example that I have already told that when we are dealing with an we have to try the different units that I have already told that when in our previous lecture that in order to meet the load demand that we have tried the different unit combination. Uh, Now, the one of the important phenomenon that when we consider that particular purpose, we haven't considered the conception of spinning reserve that we already want to meet the 550 load demand. So which unit we have to turn on and which unit we have to turn off that we have already seen that in order to obtain the 550 load demand in a supply that uh, in order to meet the 550 load demand which units or the combinations of the unit that we have tried and we have tried to meet the load demand using those particular 550 megawatt load demands by trying the different types of units and to recapture our memories that we have done in our previous lecture. In order to meet those load demands, we have tried all three combinations of the units and we are just which economical approach or the economic load dispatch approach with the help of that particular economic load dispatch approach, which combination of the units are feasible and how many costs are required that we have already seen. Now, let us take another example that suppose a power system consists of two isolated regions. One is called the western region and one is called the eastern region. So it is clear from that picture that region has three units, that is unit 1, 2 and the 3. And eastern region has two units, units 4 and the 5. So they have been committed to a western region and an eastern region. Five units as shown in the figure 1. These five units that we have already shown have been committed to supply a 3090 megawatt load that they have to supply. If two regions are separated by a transmission tie line that can together transfer a maximum 550 megawatt in either direction. So these two units are separated with the help of a tie line that can supply maximum 550 megawatt in either direction. Either direction means from western region to eastern region or to eastern region to western region. This is also shown in the figure 1. So the question will arise that what can we say about the allocation of spinning reserve in the system? So first, again understand the basic problem. The problem is that there are two regions. One is called the western region and one is called the eastern region. And in case of the western region, there are three units, units 1, 2, and the 3. And in case of the western region, there are three units, units 1, 2, and the 3. And in case of the eastern region, there are two units, units 4 and 5, and they are separated by a tie line that can transfer by a transmission tie lines. That is the transmission tie lines. They are separated, and this can transfer the maximum 550 megawatt power in either direction. So, how the conception of spinning reserve or the allocation of the spinning reserve will be there in this system? This is our question. So, let us concentrate on the particular table. It is given that is the region western and the eastern. So we have seen that western has three units, 1, 2, and 3, and their unit capacity is 1000 megawatt, 800 megawatt, and 800 megawatt. And it is that 4 and the 5 are the two units in the eastern region, and their capacities are 1200 megawatt and 600 megawatt. So the total, there are five units, and the total capacity of that five units is that 4400 megawatt. Now we have to meet the load demand of an that we have seen 3090 megawatt. So load demand, that unit output capacity in megawatt, that is the output capacity for the unit 1 is 900, unit 2 is 420, unit 3 is 420, unit 4 is 1040, unit 5 is 310. That is means 1000 minus 900, that is 100, is the spinning reserve of unit 1. 800 minus 420 is the 380, is the spinning reserve of unit 2. 800 minus 420, that is 380, is the spinning reserve of unit 3. 1200 minus 1040, that is 160, is the spinning reserve of unit 4. 600 minus 310, that is 290, is the spinning reserve of unit 5. So summation of this 5 spinning reserve is 1310, that is the total spinning reserve of that particular two systems. Now let us concentrate on the regional load demand, that is 1740, is the this summation of these three loads demands, that is the 1740, is the regional generation, that is regional generation is 1740 megawatt, and here summation of these two regional generation is 1350 megawatt. Now, say the regional load demand. This is the regional generation. Generation for the western region is 1740. Generation for the eastern region is 1350. Now, regional load demand for the western zone is western region is 1900. But western region has generating 1740 unit. So, in order to meet the 1900 load demand, this region has to take some power, or means from the eastern region, that is the conception of spinning reserve. Means eastern region first meet their load demand. Eastern region first meet their load demand, that is the 1900. That is 1900. That is the load demand of eastern region. But just to understand it, what is the load demand for the eastern region? 1900. What is the generation of the eastern region? 1350. So it can easily meet the load demand of 1900. After meeting the load demand, how many reserve is there in the eastern region? That is 1350 minus 1900, that is 160 megawatt. 1350 minus 1900, that is 160 megawatt. The load demand is there within the eastern region. 1350 minus 1900. Now, in case of the western region, what is the regional load? 1900. And what the western region is generating? 1740. So, what is the deficiency? Deficiency is 1900 minus 1740. That is also 160. That is also 160 megawatt. So, that means if western region had to meet the load demand of 1900, if western region had to meet the load demand of 1900, the region has to take 160 from the eastern region. And yes, the eastern region after meeting the load demand of 1190, it can capable to give 160 to the western region. Now another conception will come. If the tie line power, that is the maximum power of the tie line, is sufficient enough to take this 160 from the eastern region, the answer is yes, because the capacity of the tie line, that is connected tie lines that connected those two regions, are 550 megawatt. It is far than the 160 megawatt. So eastern region can transfer 160 megawatt through those pipeline to western region. That is the conception of the spinning reserve. That spinning reserve, amount of spinning reserve is there. It can sufficient to transfer through the tie line to the western region in order to meet the load demand of the western region. So it is clear that the western region, that is interchange, that is 160 is in, that 160 is out from the eastern region. But let us concentrate on in another way. If unit 4 is out of the system, if unit 4, and say the, let us take that the, say when the unit 4, if the unit 4, that is the maximum generation that is done among the 5 units, that is 1200 megawatt. Say if unit 4 is out of the system, or unit 4 is lost. So if unit 4 is lost, means only unit 5 is running in the eastern region, so it is generating 600 megawatt, but the load demand is 1190 megawatt. So 1190 minus 600, that is 590 megawatt. So this 590 megawatt is required from the western region. Okay, so but so this is seen that the spinning reserve of western region is such that it is beyond the. So what is the spinning reserve? This 380 plus 380 plus 100, that is uh, that, that is the total spinning reserve. That is 380 plus 380 plus 100 of the, that is 860. That is the total spinning reserve of the western region, which can sufficient enough in order to meet the 590 load demand that is required in the eastern region. But again, the maximum power that can be transferred through the tie line is 550 megawatt. So here the eastern region is required 590 megawatt. The spinning reserve of the western region is 860 megawatt. It is sufficient enough to meet this requirement of the eastern region, so that eastern region can meet the load demand, but they are connected through the tie lines, which can maximum power can be supplied uh, through those tie lines at 550 megawatt. So this 590 megawatt cannot be transferred to the eastern region. So when the unit, so therefore the loss in the unit 4 cannot be covered enough to the entire system. Cannot be covered enough, though the entire system has a ample reserve. So, so the only solution to this problem is to commit more units to operate in the eastern region. So it is, so we have already cleared about the, what is the spinning reserve and how the spinning reserve is operated in a system and why the spinning reserve is required. So now we will concentrate on the thermal unit constraint. Another unit constraint is called the thermal unit constraint. So thermal units are usually required few to operate them, especially when turned on and turned off. A thermal unit can undergo only gradual temperature changes. So the main factor is related with the thermal unit are the gradual temperature changes. And these translate into a time period of some hours required to bring the unit online. So it will require some time or some hours specified time period to bring all the units into online. So a thermal unit can undergo only a gradual temperature changes. As a result, such restriction in this operation of thermal plant, various constraints are arise in case of the thermal plant. So one is called the minimum uptime. Once the unit is in running, it should not be turned off immediately. So this is called the minimum uptime. So once a unit is in running condition, it should not be turned off immediately. It will take some time to turn off that particular unit. This is called the minimum uptime. Minimum downtime is known as once a unit is shut down, it may not be started immediately. So once a unit is shutting down, it will give some time to the units, then it will be started. This is called the minimum downtime. That is once a unit is shut down, it may not be started immediately. Another is the crew constraint. That is, if a plant consists of two or more units, they can they cannot both be turned on at the same time, since there are not enough crew members to attend both units while starting up. So when a plant consists of two or more units, they cannot both be turned on the same time, since there are not enough crew members to be attend the both units while they are in the starting up condition, or while they are starting up. In addition, because the temperature and the pressure of the thermal unit must be moved slowly, a certain amount of energy must be expended to bring the unit online. This energy doesn't result in any megawatt generation from the unit and is brought into the unit commitment problem as a startup cost. So these energy are generally required in order to brought into the unit commitment problem as a startup cost. The startup cost can vary from maximum cold start value to a much smaller value if the unit was only turned off recently and still relatively close to operating temperature. The first allows the unit's boiler to cool down and heat back to the operating temperature in the time for a scheduled turn on. The first thing that is the allowed the starting case of the startup pause, the first thing that is allowed the unit boiler to first cool down and then the heat back up to the operating temperature in time for a scheduled turn on. The second called the banking the second is called the banking, that is requires the sufficient energy to input to boiler to just maintain operating temperature. In order to maintain the operating temperature, the sufficient energy that is to be input to the boiler is known as banking to maintain the operating temperature. The cost of the two can be compared so that, if possible, the best approach, that is cooling or banking, can be chosen. The best approach, that cooling or banking, can be easily chosen. The first one is the units boilers to cool down, allows the units boilers to cool down and then heat back up to the operating temperature in time for a scheduled turn on. The second one, called the banking, that is requires sufficient energy be input to the boiler to just maintain the operating temperature. So the startup cost when the cooling is given that Cc into 1 minus epsilon minus T to the power minus T by alpha into F plus Cf, where C suffix C stands for cold start cost, MBTU, F is the fuel cost, C suffix X is the fixed cost. This includes Q expenses, maintenance expenses. Alpha is the thermal time constant for the unit. T is the time hour in units was cooled. Startup cost when banking is equal to C transpose T into T into F plus Cf, where Ct is the cost, that is MBTU per hour of maintaining unit at operating temperature. So this is the startup cost. This is the general equations for the startup cost of cooling and startup cost when tanking. So finally, the capacity limits of thermal units may change frequently due to maintenance or unscheduled outage of various equipments in the plant. This must also taken into account in unit commitment. So now let us is the hydro constraint. One of the important factor is the hydro constraint. It is that unit commitment cannot be completely separated from the scheduling of hydro units. We have to consider the scheduling of hydro units. The thermal units that we have already seen, the hydro units also be considered when we do the unit commitment. In this text, we will assume that the hydrothermal scheduling or coordination problem can be separated from the unit commitment problem. So this is the figure of time-dependent startup cost, the cost for the banking, and the cost of the cooling is the startup cost. The figure for the time-dependent startup cost. So the another is called the must run. Some units are given a must run start status during the certain time of the year for a reason of voltage supports on the transmission network. Means some unit must run, that they have to run in order for a sometime certain times of year in order to voltage support on the transmission network, or for such purpose as supply of steam for uses outside the steam plant itself. So these units must be run in order to provide the voltage supports on the transmission network, or for such purpose as supply of stream for uses outage the steam plant, for uses outside the steam plant system for the purpose of supply the stream. So those units are must in the running condition for a certain times of the year. Fuel constraint, a system in which some units have limited fuel or else have constraints that require them to burn a specified amount of fuel in a given time, presents a most challenging unit commitment problem, is a fuel constraint. So today we have learned about the different constraints that are associated with the unit commitment, and how, and the conception of spinning reserve, and how the spinning reserve is applied to an entire system, that we have seen that system of two regions where they are connected through a tie line, and also the conception of hydro constraints, that is the unit constraint, hydro constraint, mass run, and fuel constraint. Thank you.